Here's a formula so simple you could write it on a napkin. Take a number between 0 and 1. Multiply it by 1 minus itself. Then multiply by a knob we'll call r. That's it. Feed the answer back in again and again. And somehow that tiny loop, grade school algebra, can explode into pure, unpredictable chaos. The story starts, of all places, with the weather. Back in the 60s, Edward Lorenz was running early computer forecasts. And he noticed something unsettling. Round the starting numbers off just a hair and the forecast would drift and drift until it was completely different. A tiny cause, a giant effect. That's the seed of what we now call chaos. To see how chaos hides in something so plain, start with a model of population growth, the logistic equation. Solve it smoothly, and populations just glide up to a steady level. But the moment you solve it on a computer step by step, you get a recurrence. And with the right change of variables, it collapses to this xn plus 1 equals r times xn times 1 minus xn. Geometrically, the map is just a parabola. It takes the interval from 0 to 1 and folds it back into itself. The knob r sets how tall the hump is, from a gentle mound up to a steep arch when r hits 4. Everything that follows comes from turning that one knob. Now, where does the sequence settle? At a value that maps to itself, a fixed point, where the parabola crosses the diagonal line y equals x. Solve it and there are 2, 0, and r minus 1 over r. So the natural resting place of the population is r minus 1 over r. At least when it's stable. Here's a lovely way to watch the iteration. The cobweb. From your starting point, go up to the parabola, that's your next value. Then across to the diagonal to feed it back. Up, across, For a gentle r, that staircase spirals inward, homing right in on the fixed point. The population settles down. Whether the staircase spirals in or flies out is decided by one number. The slope of the parabola at the fixed point. Nudge the sequence a tiny bit off. Each step, that nudge gets multiplied by the slope. If the slope size is under 1, the nudge shrinks away and you converge. Over 1, it grows and you're thrown off. For our fixed point, that slope works out to exactly 2 minus r. So the fixed point is stable exactly while the size of 2 minus r stays under 1. That is, while r is between 1 and 3. But push r past 3, and the slope tips over the edge. The resting point goes unstable. The staircase can't spiral in anymore. And instead of settling on one value, the sequence starts hopping between 2. That's called period doubling. One value splits into 2. And it doesn't stop. Crank r higher, and each of those 2 splits again into 4. Then 8. Then 16. The splits come faster and faster, piling up toward a magic threshold near 3.57. And here's the jaw-dropper. The gap before each doubling shrinks by the same factor every time, about 4.669. Measure it in the logistic map, measure it in a dripping tap, in a heart rhythm, you keep getting the very same number. It's a universal constant of chaos, called Feigenbaum's constant. Past that threshold, the doublings have piled up into infinity, and order breaks down. The sequence stops repeating altogether. At r equals 4, the iterations wander across the whole interval, never landing, never cycling. That's full-blown chaos, from a single parabola. Now put it all on one picture, the bifurcation diagram. Along the bottom, the knob r. Up the side, where the sequence settles for each r. Sweep from left to right and watch the whole saga unfold. One branch, then 2, then 4, then a shimmering cloud of chaos. But look closer. The chaos isn't solid. Slice into it and you'll find clean gaps, windows of order. The most famous, near 3.83, snaps back to a tidy cycle of period 3. And zoom into any corner of this diagram, and you find smaller copies of the whole thing. It's a fractal, self-similar all the way down. So that's the secret hiding in one line of algebra. Nonlinearity and nothing more is enough to breed chaos. A straight line rule never could. And there's a warning tucked inside. If you're solving a smooth equation on a computer and your step is too big, you can conjure chaos that was never really there. Sometimes the wildness isn't in the world. It's in the math.